So before we get straight into the business of tidal waves, I think I would like to tell the story of Newton's apple. I think we touched on this topic a little bit the other day. There is a famous story that Newton was sitting under an apple tree and an apple fell on his head. That story is most probably an apocryphal. The word apocryphal means old stories fabricated by men and then exaggerated over time. Such an incident actually never happened. All Newton himself said was, I was just sitting under an apple tree and I was just occasioned by the fall of an apple. Right? So the apple actually didn't fall on Newton's head. So the first thought that ran in Newton's mind was, he was looking at the apple and he saw the apple getting accelerated. So the apple's initial velocity was 0. And then all of a sudden the apple is getting accelerated. So he thought that there is an acceleration. If there is an acceleration, there is a force that should have associated with that acceleration. So he called that force gravity. So the first thought that ran in Newton's mind was, he was able to find that the apple is getting accelerated. And because of that acceleration, there is a force, and he called that fictitious force, gravity. The second thought that ran in Newton's mind was, he imagined the apple tree to be twice as high as its original height. If the apple tree is twice as high as its original height, still one would expect the apple to fall from the tree, yes or no? Right? Just imagine an apple tree that is twice as high as its original height. Still one would expect the apple to fall from the tree. That was the second thought that ran in Newton's mind. The third thought that ran in Newton's mind was quite revolutionary. That is, he thought, if this force called gravity can reach the top of the tallest tree, he asked this question, might it not reach all the way to the surface of the moon? Which means moon's orbit around our planet Earth could be the result of gravity. That was the third thought that ran in Newton's mind. It was revolutionary. That is, if this force called gravity can reach the top of the tallest tree, might it not reach all the way to the surface of the moon? Which means moon's orbit around our planet could be the result of gravity. And the converse is equally true. That is, Earth's orbit around Sun could be the result of gravity. And he was able to give a very concrete law of gravity. So can you just tell me what is Newton's law of gravity? Every object attracts every other object with a force that is directly proportional to the product of two masses and inversely proportional to the square of the distance between them. So in simply said that if the distance between the two objects doubles, gravitational force decreases by a factor of 4. If the distance between the two objects triples, gravitational force decreases by a factor of 9. If the distance between the two objects quadruples, gravitational force is going to decrease by a factor of 16. Right? If the mass of the object doubles, then the gravitational force is going to increase 2 times. If the mass of the object triples, gravitational force is going to increase 3 times. If the mass of the object increases by 4 times, gravitational force is also going to increase by 4 times. Right? So there is a very straight relationship there. So that is Newton's law of gravity. So the reason why we touched on this gravity is this topic is very, very pertinent to our topic under discussion. That is tidal forces. Can you just tell me what causes the tidal force? Now we are into the topic. What causes tidal waves? It is the gravitational pull of what? So gravitational pull of moon is going to cause this tidal waves. So why not gravitational pull of sun? Why is that gravitational pull of sun is not going to cause the tidal waves? The usual answer is, the sun is very far. Sun is 90,000 million miles. 90,000 million miles away from Earth. So sun is at a certain distance, a very large distance, which means that the gravitational force of sun exerted on Earth is going to be weak. That is the usual explanation that is given, because moon is closer, even though its mass is small, moon is actually closer to Earth, so it causes waves. But is that explanation correct? We have to check it. We have to check that data, right? We will do a small calculation to find out whether that is actually true. If it is not true, then we have to find out what exactly causes the tidal wave. So let us check this. Okay? Fine. Can you just tell me what is Newton's law of gravity once again? Please tell me that equation. F is equal to capital G capital M, small m divided by r squared. We will keep this capital M as mass of the earth, small m as mass of the object, right? In our case, it is going to be mass of moon, so I will just add a suffix m right there. R is the distance between earth and moon, so I will just add another suffix m here. So can you just tell me what is... Okay, this is the gravitational force that is exerted by moon on earth. So that is the formula. Is that okay for everyone? Right? The gravitational force that is exerted by moon on earth. So what I have written is fine. Everybody's fine with this? Yeah. So I'm going to write another formula that is gravitational force that is exerted by sun on moon. So I'm going to write on top of that this equation, that is gravitational force that is exerted by sun on earth. I'm sorry, not moon. Gravitational force that is exerted by sun on earth. So can you just tell me what is going to be that formula, please? Capital G, capital M, small m, suffix s divided by r s squared. You can respond. It's not a problem. Right? So can you just tell me, please? That is the gravitational force that is exerted by sun on earth. Is that fine for everyone? Right? So we are just going to divide these two equations. Go ahead and divide these two equations. Get rid of the constants. And tell me what is that you are going to get. Fs divided by Fm is equal to, can you just tell me the values, please? G goes away, capital M goes away. Can you just tell me what is that you will be getting? Mass of sun divided by mass of moon into, yeah, tell me, guide me please. Rm divided by Rs, the whole square. Now all we need to know is the value of Ms by M. Ms divided by Mm. I think I have got the values. You can just tell me those values. And all we need to know is the value of Rm divided by Rs whole square. You can now tell me what is the value of Ms divided by Mm. Yeah, it is 226 8 0 0 0. Okay. That is this value. This value is given here. Can you just tell me what is Rm divided by Rs? There it is given as Dm divided by Ds. Still you can make it. Yeah. Go ahead, no problem. 1 by? So it is Rm divided by Rs. It is Rm divided by Rs. 1 divided by 390. The whole. Am I right? Yeah? If you have got a calculator, can you just feed these values and tell me what is the answer that you are getting? You can be casual. Yeah. Can you just go ahead and tell me the values that you are getting? Okay, what is the value that you are getting? I think Panram, you said the answer? 176.19. So what is the force that is exerted by sun on earth when it is compared to the force that is exerted by sun on... I'm sorry. What is the force that is exerted by sun on earth and you compare it with the force that is exerted by moon on earth? It is very clear, very obvious, very explicit. I can use this word, very axiomatic from this equation. That is, the force that is exerted by the sun on earth is 176 times greater than the force that is exerted by moon on earth. So the answer to the question, the first question, that is, the force that is exerted by moon is on earth is going to be greater because moon is closer to earth is actually wrong. But it is the moon that causes the waves. So where do we go wrong? Where do you think is the missing link? Where do you think is going to be the missing link? Everybody is able to understand this? Yeah? So we have got a missing link here. Something is wrong in our understanding. What we learned in our textbook is actually wrong in our school, right? In our school, if we say that the force that is exerted by moon on earth is going to be greater than the force that is wrong. So can you just tell me what is going to be the correct statement? What is the missing link? What is that? Something it has got to do with the revolution of moon. Yeah. But let us look very carefully, right? The scenario, what is actually taking place? Moon is revolving around Earth. That is true. So I'm going to draw the picture here. This is our planet is here, Earth, and the moon is here. Now, moon is revolving around the Earth is actually that statement. If I have to tell that statement, that moon is revolving around the Earth, that statement is wrong. That statement is not true. I have to tell that statement, I have to define it with its precise shade of meaning. That is, moon is not actually orbiting around Earth. That is wrong. This is moon, and if this is Earth, moon is not actually orbiting Earth. Actually, they do have a common center of gravity, common center of point. We call it a center of gravity. The two put together, they have this common center of gravity. So moon is actually orbiting around this common center of gravity. So I'm putting a star here to represent that common center of gravity. So moon is actually orbiting this common center of gravity. So it should be an ellipse, actually. I'm trying my best. Moon is actually orbiting the common center of gravity. So you are able to understand this? So strictly speaking, moon is not actually orbiting the Earth. Moon is actually orbiting the common center of gravity, giving the impression as if it is orbiting the Earth. And what is the Earth doing? It is rotating about its own axis. That is why we get this night and day. We know that. Okay? Then it revolves around sun. Okay? Okay? It is the same principle. But point here is, Earth is also rotating about the center of gravity. That is true. So it is not only moon that is orbiting around that common center of gravity, but Earth is also spinning about its common center of gravity, about that common center of gravity, where I have put a star over there on that blackboard. Earth is also spinning. Okay? Tom is fine with this explanation, right? Earth is also spinning about this common center of gravity. Is that okay for you? Right? But it happens in such a way that Earth's center of gravity, I'm sorry, not Earth's center of gravity, the common center of gravity is not away from Earth, it's not outside of Earth, it is here. So I have to redraw this picture. That is, the common center of gravity is not here, but it is just inside, at a distance of, say, 0.72 times the radius. Right? At a distance of, say, 0.72 times the radius. So Earth is actually revolving about a common center of gravity that is just inside of Earth. Maybe a little bit difficult to imagine, but it is actually happening that way. Right? You have to exercise it in your imagination. It is actually happening that way. You are able to understand this point? Yes? It is actually happening this way. Right? And the moon is actually revolving about the common center of gravity, giving the impression as if moon actually revolves around Earth, but both of them are actually revolving. And if you ask me the question whether, what about sun and Earth? It is the same. Sun and Earth, they have got the common center of gravity, right? And actually they are revolving about that common center of gravity, right? It is happening that way. Okay? Fine. Now, what is causing the bulge? What is causing the tidal waves? That is the question that we have to ask. So I'm going to represent the hydrosphere here, this shaded region. This shaded region. The shaded region indicates the hydrosphere. What do you mean by that? The ocean that is represented here, right? So what is causing the tidal waves is the question. And it is an easy question to answer. It is an easy question to answer, right? What is causing the tidal waves? The answer to this question is the answer to the fall of 10,000 mile man. Everybody knows that analogy. If you have a man whose height is 10,000 miles and if he is falling, can you just tell me what would happen to the height of this person? The height of this person is 10,000 miles, and if he is falling toward here, can you just tell me what is the stress that he is going to experience? So he is going to experience tensile stress. This person, the height is 10,000 miles. 10,000 miles. So his feet is being pulled toward earth at here with a greater acceleration than his head. So what is going to happen is he's sort of getting stretched. That is the reason. So which means that if you apply the same principle here, the earth is getting attracted toward moon, yes or no? To be very precise, the earth is getting attracted, the earth is spinning, the earth is revolving, to be very precise, with a certain acceleration. Certain, what I'm saying is, the earth is getting attracted toward, not toward moon, the earth is orbiting around that common center of gravity. Of course it is orbiting around that common center of gravity, which means that the earth is also falling. It's not only that moon is falling toward the earth, it is also true that the earth is falling toward the moon. In the sense, it is revolving around the common center of gravity. If that is the case, right, if you apply the same analogy here, this part is getting accelerated in this direction. With a greater acceleration, let us say that this is point A. And at this point, the opposite to the point A, let us call that as point B. That point B, which is opposite to the point A, that is getting accelerated toward moon with a smaller acceleration. Is that okay for you? Fine. That statement, if I make, is that okay for you? So if you look very carefully, this point A is getting accelerated toward moon with a far greater acceleration compared to this point. So what should happen to you? What should happen to the hydrosphere? What should happen to the hydrosphere? Please tell me the answer, please. It gets stretched, right? The hydrosphere should get stretched, which means that that is the reason why you get this bulge, right? There is a reason why you get this bulge. And this is the tidal wave. Is that okay? This is the tidal wave. So the reason for tidal wave is because the earth is falling toward moon in the same way that the 10,000 mile man is falling toward the earth. And it is sort of getting stretched. And we have not yet answered the question, the first question. Why is that sun is not causing the tide, but rather it is the moon that is causing the tide? We will have that discussion after a short break for 2 minutes, right? Can we have a break? Okay, the question now is not yet answered. That is, to some extent we are able to answer what causes the bulge. I said that it is because of earth revolving, earth falling toward moon, to be very precise, and moon falling toward earth, right? So that is the reason why this bulge is happening, right? The next question is, why not sun that causes the bulge? Why is that the moon is causing the bulge? That is the question that we have to answer. Why not the sun is causing the bulge, and why the moon is actually causing the bulge? That is the question that we have to answer. So let me try to answer that question. Let us consider 2 points, A and B. We will first work for moon now. Can you just tell me what is the force of attraction, gravitational force of attraction for the point A? You can just tell me the equation, please. Tell me the equation, please. Yeah, it is the Newton's law of gravity. There is not going to be any special equation. It is the same equation. Go ahead and tell me the equation. Capital G, capital M, small m, suffix m, because it is for moon, divided by It is r squared, but what I'm going to do is, it is the distance minus this distance. Suppose if this is capital D, so this distance from the point A to capital D, from the point A to this point, it is going to be capital D minus R. So it is capital D minus this radius whole square. That is, to be very precise, capital G, capital M, small m divided by the distance square. Can you just tell me what would be the gravitational force expression for the point B? Can you just say this please? Capital G, capital M, small m, suffix m divided by capital D plus R the whole square, because it is this distance now, from the point B. This distance, I think it is capital D plus R. Okay, fine. Now what we have to do is we have to find out what is FA minus FB. We have to work this equation. Can you just tell me what is FA minus FB is? It is capital G, capital M, small m, suffix m, minus, can you just help me with this please? Capital M, small m, small m, divided by D minus R the whole square into D plus R the whole square. Okay? I can write this equation as, can I just take this one common outside please? What is that I will be getting? So, what is that? Is it, what I have written is wrong? What is the mistake? Okay, cross multiply. If I take this outside, capital G, capital M, small m, suffix m. Can you just cross multiply and tell me please? Capital D plus R, the whole square, minus S please. Capital D minus R, the whole square. Is that okay? Yeah. Can you just simplify the numerator and tell me the answer? One of you. Simplify the numerator and tell me the answer. Go ahead, simplify the numerator and tell me the answer. What is that? Simplify the numerator and tell me what is that you will be getting for the numerator. Capital G, capital M, small m, suffix m. What is that you will be getting for the numerator? Okay, 4 capital D R divided by, how can I simplify the denominator? Any idea please? It is of the form of A plus B into A minus B whole square. Yeah, exactly, fine. So it is of the form A plus B, A minus B whole square. So it is A squared minus B squared the whole square, right? So can I write, you will allow me to write that directly. It is A squared, which is A squared, okay, A plus B into A minus B. A squared minus B squared the whole square. Is that okay? Yeah? Fine. Okay. Can you just help me do the next step please? It is capital G, capital M, small m, suffix m. Can you take this D outside? Of course you can take it into 4R divided by, can you just take this capital D squared outside? What is that you will be getting? D power 4 into 1 minus R squared divided by D squared the whole square. Okay, so this and this goes away. So I can rewrite this expression as capital G, capital M, small m, suffix m divided by D cube into 4R divided by 1 minus R squared by D squared the whole square. I want you to tell me what is the value of R by D, the whole square. I think you can refer. It is 1 by 60, 1 by 60. Can you just feed this value? R by D is 1 by 60. Can you just tell me R by D is 1 by 60, so it is 1 by 60 the whole square. So 1 minus 1 by 3600, the whole square. So what is the value that you are getting? It is capital G, capital M, small m, suffix m, divided by dq into. Can you just tell me this value, please? What is this value? If you are putting 1 by 60, just go ahead and use your calculator and tell me, please. Use your calculator and tell me. R by D is 1 by 60. 1 by 60 the whole square. So it is 1 by 3600. 1 minus 1 by 3600. The whole square. So it is 0.9999, which asymptotically converges to 1. So this value becomes 1, which means that into R. Right? This is the final expression for the differential forces of attraction between, this is the expression for the differential force of attraction, which means Fa minus Fb between moon and earth. Right? Now we have to find out the differential force of attraction between sun and earth. And we have to compare that, right? So take down this, we are going to compare the differential force of attraction between sun and earth. So this is the expression for differential force of attraction between moon and earth. Okay. So there you can see the differential force of attraction, Fa minus Fb, that is the differential force of attraction between moon and earth. Now I am going to write the differential force of attraction between sun and earth. One of you can tell me the equation right away. One of you can tell me the equation right away. Just by looking at that final expression, it is going to be the same, but except for the notations. Can you just change the notations and read the final result, please? Yeah, exactly. Capital G is going to be the same. It is universal gravitational constant. Capital M, mass of the earth, is going to be the same because it is the attraction between sun and earth. Small m suffix s, which stands for mass of the sun, divided by the notation d. If this is the notation d, it is the distance between earth and moon. Here I have put ds, right? ds cube, just to change this. And what about this r? R is going to be the same. So this is the expression for differential force of attraction between earth and the sun. There you can see the expression for differential force of attraction between moon and earth for a while. There you can see the differential force of attraction between moon and earth. There you can see the differential force of attraction between sun and earth. Right? Now I am going to divide the two equations to find out which one is going to be greater. Right? So I can call this as equation number 1, if you wish. I can call this as equation number 2. I'm just going to divide them. So help me divide the equation, please. Help me divide the differential force of attraction. Force of attraction. I'm putting dF, differential force of attraction between moon and earth, right? Between moon and earth, divided by the differential force of attraction between sun and earth. You just have to divide 1 and 2. So go ahead and do that for me, please. Do that for me, please. Read that for me. One of you please go ahead, read that for me. Rajkumar. Capital G, capital M, small m, suffix m, capital R, divided by D suffix m, whole cube, into, I'm dividing, so go ahead please, you can do it. ds cube divided by capital G, capital M, small m suffix s into r, so r goes away, g goes away, capital M goes away. All I have got now is mass of the moon divided by mass of the sun into distance between sun and earth divided by distance between moon and earth, whole cube. Now you can refer the table and you can just tell me the values. We will feed the values. We will feed it in the calculator. We will calculate it. So m divided by ms. It is 1 divided by 268 00 000, right? For a while. Yeah. Just for a while, please be patient. Yeah. You can cut it later, right? But now, just please be quiet for a while. Yeah. Into 390 cube. Can you just use your calculator and tell me what is the value that you are getting? What is the value that you are getting? What is it? Yeah, someone said the answer. Yeah, 2.21. Look at this value, and now we have got the answer to our question. That is, if you look at this value 2.21, the value 2.21 means that the differential force of attraction between Earth and Moon is 2.21 times greater than the differential force of attraction between Sun and Earth. So, driven by data now, it is quite obvious that tides are predominantly caused by Moon. Not because the gravitational force of attraction between Earth and Moon is greater, but because the differential force of attraction is greater. The differential force of attraction between Moon and Earth is 2.21 times greater than the differential force of attraction between Sun and Earth. That is the reason, right? That is the reason for the tides, right? Okay, the next topic there is, but won't there be any effect of Sun on the tides? Suppose, let us imagine this way, the situation is, listen everybody. Imagine this situation where you have got Sun here. Just imagine the Sun to be here. Now they are working in opposites. What would happen to the tides during the eclipse? I think there is a book by Stephen Hawking, Theory of Everything. The book starts with this phrase. That is, it starts this way. In the book On the Heavens, Aristotle was able to put forward two good arguments for proving that Earth is a round ball rather than a flat plate. Right? The first argument Aristotle was put forward was the Earth's shadow on the Moon. Suppose if this is Sun is here, the Earth's shadow on the Moon is always round. That was the first argument that was put forward by Aristotle. If Earth is a flat plate, for example, then the shadow would have become elongated or elliptical, but the shadow is always round. So which means that would be true only when Earth is a round ball. So Aristotle in his book On the Heavens was able to prove that. But my question here is, what would happen now if Sun is here? What would happen to the tides? Would the tides cancel out, or the tides effect would be more pronounced? Understand my question now, everybody. Sun is here. Imagine Sun is here. Sun is pulling. Moon is also pulling. So my question here is, what would happen to the tides? Will it recede away, or what is going to happen? Tides will still be there. My question is, what about the effect of sun on the tides? What is that? No tides, no. Effect will be?
The strength of the tides will be different on different that.
The strength of tides will be?
Opposite.
A sun is here.
At point B, the strength will be less, and
at point B, the strength is going to be
less compared to point A.
Okay, but Oliver, if you look very carefully at this explanation, everybody listen here. Listen here. There is sun is here. So it is pulling. Moon is pulling this way. This bulge is caused because of stretching. This bulge is automatically happening because of moon is pulling and there is a stretching. And the sun is also pulling this bulge. Which means making this bulge more bigger. Causing this bulge even bigger. So when the sun is here, this bulge gets bigger. Right? This bulge gets bigger. So the fact that the presence of sun opposite to the presence of moon, the fact that it is going to cancel out the tides or it is going to make the tide less severe is not true. Actually, during the time of eclipse, the bulge is going to be high. Because during the time of eclipse, the bulge is high, right? What is actually going to happen is the tides will be very high. The tides that is going to be very high. So in the open sea, the tide is going to be very high. Say for example, let us say 3 feet, 4 feet, or even 5 feet. That height is not sufficient for generating electricity. Now we are into tidal power. Slightly we are introducing the topic. That height is not sufficient for generating electricity. So what should actually happen? What is actually happening there? The tide that is created in the open sea is not sufficient for generating electricity. So what should actually happen? In the open sea, the tide is low. But as the tide approaches toward the shore, what is happening? The tide height actually, why do you think that it's increasing?
It hits the surface of the ground.
Because
Because
there is a shore automatically. Obviously, it is being pushed up, and there is a kind of a very big tide. Even there is a place called Bay of Fundy in Canada, right, where the tide even approaches 30 feet, right, 35 feet, right, which means that is sufficient for generating electricity.